Dr. B here, and let's solve 6 different rate law problems. Let's start with number 18 here. Determine the rate law and the rate constant. In trial 1, they have a couple of concentrations, and there's your rate. In trial 2, they double the rate of the first reactant, hydrogen, while keeping the oxygen constant. Concentration doubles, rate doubles, it's first order with respect to hydrogen. In the second one, they're going to keep hydrogen constant. So I think we're looking at trials 1 and 3 there. They double the oxygen and the rate quadruples. That is second order with respect to oxygen, since 2 squared equals 4. So the rate is first order with respect to hydrogen, second order with respect to oxygen, third order overall. To solve for K, pick any trial. I always do the first one and plug in. Rearranging, we can see that K must equal rate over the concentrations of the reactants. Don't forget about those exponents. So it would be, the rate is 0.04 divided by 0.6 times 0.3 quantity squared. And that would show that the rate constant is 2.22, and that looks like 1 over, I believe it should be, that's molar squared over 1 over molar per second instead of molar squared. Okay, for example 2, A plus B turns into products. They're doubling A while keeping B constant in trials 1 and 2, but this leads to a fourfold rate in reaction rate, therefore I believe it's second order. I'll say it again. Doubling the concentration leads to a fourfold increase in rate, therefore second order. 2 squared equals 4. And here's trials 2 and 3 where they keep the A constant, which is good, we already know it. And they double B, and that also makes it 4 times faster. It is second order with respect to each reactant. K would equal 0.04 divided by each of those squared, which is 1.23 molar cubed per second. In question number 20, again, A plus B goes to products. Keeping A constant here, but tripling B leads to a tripling of the rate. Therefore, for B, it is first order. What about for A? Let's look for the trials where B is held constant. That's trials 2 and 3. And doubling A leads to a doubling in the rate. I would say it's first ordered with respect to each. K is going to be equal to, if you take trial 1, 0.1 over 0.1 times 0.1. And that is 10 molar per second. 10 per molar second. You know, for the units, you have to just see what spits out, right? Molar per second over molar times molar equals 1 over molar times second. So just do the unit conversion for finding the rate constant. There is one, and it's going to vary depending on the exponents. For trial 21, we have A plus B turning into products, and tripling A while keeping B constant doesn't do anything. Hey, look at this. No matter what they do, the rate is always the same. And in the trial 2, I think they are keeping A constant for 2 and 3 and really increasing. I don't even know by what fold B, but it doesn't matter because it has no effect. It is 0th order with respect to each. So you could simply, the rate equals K. And then K4, therefore, is 0.04 molar per second. 2 more. Number 22 is a fill in the blank. We want to come up with some data such that the rate will be first order for each. So I see that the rate's doubling in the trials 1 and 2 while they're holding B constant. So let's double the concentration of A. That will make it double the concentration, double the rate, first order. And similarly for B, trials 1 and 3 look like they're holding A constant, which is good, but it's increasing fourfold, so I better increase the concentration fourfold. Quadruple the concentration, quadruple the rate, that is first order with respect to B. K would be equal to, for trial 1, 0.04 divided by 0.3 times 0.3. And that is 0.4 over molar second. For the last one, we want it to be, wow, second order for A and third order for B. Now, nicely, they're holding B constant for trials 1 and 2. So I want it to be second order, and it's increasing fourfold, so I better only increase the rate by a factor of 2. Doubling the concentration quadruples the rate. 2 squared equals 4. Now, third order for B. Oh boy. Well, let's look for those two trials where A is held constant. That's 1 and 3. And this is going up 8-fold. So that works out nicely if I double the concentration, since 2 to the third power is 8. So as we go from 0.4 molar to 0.8 molar, we double the concentration. The rate increases 8 times. 2 to the third is 8. And K would be equal to, for trial 1, 0.04 divided by 0.2 squared times 0.4 cubed, which is 31 per molar to the 4th seconds. That is 6 different examples of solving rate law.